Let us try an example to check for the stress limit of a pre-stressed beam. The beam is simply supported over 25 meter span. It is subjected to an UDL of GK 10 kN per meter and QK 7 kN per meter. The dimensions of the cross sections is given here. There is an tendon there, which is placed at 200 mm from the bottom of the beam. That gives an eccentricity distance from the neutral axis of the cross sections. The eccentricity will be the same throughout the beam as the tendon profile is straight. The concrete strength is 50 at the surface state. Its concrete strength is 35 at the transverse state. The prestressing load is 2750 kN, and the losses for the short term and long terms are 10% and 20% respectively. You are asked to draw the stress plot diagram in order to determine the stress at the top and bottom fiber of the beam, at the midspan and the support. Next, you are asked to calculate this stress at the transfer and at the service states. Lastly, you need to check for the stress limits where flexural crack is not allowed at the service state. You may pause the video for a while for you to work out the solution. To solve these questions, first you need to draw the stress plot diagram. The stress plot diagram for the midspan and the supports are given here. At the midspan, there will be stresses due to the axial force, bending, and eccentricity. This leads to the top fiber stress to be equals to the axial plus bending minus the eccentricity. As for the bottom fiber stress, it will be the axial minus bending plus eccentricity. As for the support here, there will be eccentricity, but the moment will be equals to 0. In this case, the contributions by the moment is not considered. That gives the top fiber stresses equals to the axial minus the eccentricity. As for the bottom fiber stress, it will be the axial plus the eccentricity. These equations outline the stresses to be checked at the midspan and at the support. To determine the stress, you need to find the relevant value and substitute into the equations. We use a spreadsheet to help us to do the computations. The GK and QK are given here. The factor of safety, it will be considered as 1.0. The dimensions and specifications have been keyed in here, and the eccentricity will remain the same throughout, and the P, it will be 2750. At this stage, you still do not know the eccentricity because you haven't identified the centroid of the section. Also, at this stage, you also do not know the self-weight of the member as you haven't really calculated the weight of the member yet. With that, we need to first determine the geometrical property of the sections. From the equation here, we need to determine the area and also section moduli. The section moduli is a function of I per y. That means we require the second moment of inertia. With that, this table is meant to generate the area, centroid, second moment of inertia, and also to determine the section moduli. As the member is made up of 3 elements, which is element 1, 2, and 3, we can create a table to quantify the area of the respective element. The Y here is refers to the centroid of the element as measured from the bottom of the beam, as indicated by the arrow here. Next, this column is produced by multiplying this column with this column. Obtain the summation of A, obtain the summations of AY. The centroid is determined by dividing the sigma AY with sigma A, as given by these equations. When you divide these two values, you will obtain this. This represents the centroid as measured from the bottom of the beam. To obtain the centroid measured from the top of the beam, you need to obtain the overall height to be minus with the centroid of the bottom of the beam. You obtain this centroid of the top of the beam. Next, you need to calculate for second moment of inertia. It is obtained by calculating the equations of BH power 3 per 12. The area already given. Now you need to obtain the dy. dy referring to the distance from the centroid of the element with the centroid of the entire beam. This is obtained by minusing this y with this. The second moment of inertia for the entire beam is given by this equation, which you need to add the effect of the area times dy squared. With that, you have to obtain the area times dy squared. This is to be multiplied with this square, you obtain this column. The summation of I plus a dy squared, it will be equals to this. The summations of all these 3 rows, you obtain this value. And this will be the moment of inertia of the beam sections. Next, you need to calculate the section moduli. It is calculated by dividing the I with the centroid of the member. For Z top, you use Y top. For Z bottom, you use Y bottom. The I will be the same. Divide I with Y1, you obtain this. Divide I with Y2, you obtain this. Next, you calculate for the stress limit. The stress limit for the compressions is 0.6 of the concrete strength. As for the tensions, during the transfer, flexural crack is allowed, therefore FCTM is used. But at the surface, the flexural crack is not allowed, so the limits for the tensions will be equals to 0. At the transfer stage, the concrete strength is lower. Therefore, a lower concrete strength is obtained. Then the compressive limit, it will be equals to 21. While at the surface limit, the concrete strength increases. This goes for the limits of the compressive stress. Next, we calculate for the loading and moment. The concrete element comprises some loading. This is calculated by multiplying the area of the beam sections with the unit weight of the concrete. Therefore, this 28 kN per meter will be considered as the self-weight of the beam, plus the service load. The UDL at service, it will be the summation of 2. The UDL at transfer, it will be the self-weight alone. Next, we calculate the moment acting on the beam. For simply supported beam, the moment at the midspan will be WL squared per 8. Substitute this value into the equations, you obtain the moment mean and moment max. Then we calculate for the stress distributions. Refer back to the stress equations here. Substitute the relevant value into the equations. For the transfer stage, alpha is used. For the service state, beta is used. For the transfer stage, M-min is used. As for the service state, M-max is used. For the top beam, Z-top is used. For the bottom of the beam, Z-bottom is used. Substitute the relevant value into the equations. You will obtain the stresses for the transfer and service at top of the beam and bottom of the beam, at the support and at the midspan as listed here. These stresses are later to be checked against the limits. The stress here has to be falling in between the two limits. Based on the calculation here, the beam will fail at the service state, at the bottom of the beam. With that, this concludes the example to solve the stress limit in the beam. When you find that the member is going to be failing at the service state, you will need to redesign the member by adjusting the dimensions of the beam, positions of eccentricity, or even the prestressing load. You could also look into the possibility of allowing for the flexural crack. That will be very dependent on the applications of your prestressing members and its exposure conditions. If flexural cracks is allowed within the member, you will need to check for the FCTM limits, and the provided amount of reinforcement bar need to be at least greater than AS mean, and the calculations of provided AS mean is inclusive of the prestressing steel area and non-prestressing steel area.